lecture, and I try to record lectures and put it on YouTube in case you need to go back. So I hope you still remember from Wednesday that if we have uniaxial stress situation, like here, if you pull on one dimension, on the other dimensions, you see also a change in dimensions. So here, for example, the stress is along z direction, and you see that you have a strain along z direction. But then, not only, you can very easily see that the blue block is a stretch in z direction, but also has been contracted in the other two directions. And we talked about Poisson's ratio. And here, for example, we have the two sides, or we can just look at epsilon x. You see that it would be related to the epsilon z through Poisson's ratio. And strain is change of length over the original length in either direction. And this was the uniaxial case. And one of the things we did last time was look at the more general triaxial case. You probably remember this one. We said, okay, if you have triaxial stress state, then you can think about it as a combination of three uniaxial stress states. For each one, you can write the strains in all three directions. In the direction of the stress, it's simply sigma over E. In the other two directions, you need to use Poisson's ratio. These negatives are not very clear here, connected to the line. And then if you want to look at, let's say, the total strain in the x direction, you have to see how much is the strain in the x direction from here, and from here, and you sum it up. To warm up, please look at your next slide and try to see if you can write down the generalized Hooke's law for all three directions. You have it in z direction or x. If you look, you can also write it for yourself in the y and z direction. And try not to look at the board. Once you are done, take a look just to check. I should shut it down? No? What? Okay, is it good? Oh, you wanted to see it? Yeah. The point is not to see it. Don't worry, I put it back up. No, the point is to see how much you can retrieve. I didn't mean to. Try to see if you can write it yourself. But it's the same formulation. It's written a little bit different. Okay. Now, if you have written this down and checked, don't be bored. Look at the example. Read it and we'll get back to that. Oh. These are the same formulations. It's just written differently. So don't worry. If you are done with all of that, look at the example in your next slide. The first thing to do, put the dimensions on the middle schematic. Read the problem, look at the shape, and put the dimensions on. example, I still put this up because some people are still writing. But in the example that you have in front of you, as I said, the first thing, look at the schematic, put the dimensions on it. Turns out to be very helpful. So you have the original dimensions of a piece of material, doesn't specify really. And you know what happens after you apply this uniaxial tension. This is only tension in one direction. And what's happening is that the 2-inch becomes larger, as you expect, it becomes 2.007, and the other dimensions, they shrink. And what I'm asking is for you to actually calculate the elastic modulus. So I guess we are good here. So this is something you need to do on your own. So when there is an example like that, typically I do not do it until 3 people have done it right. So the example that you have is this. It's a 3-dimensional block, and here is 2-inch in the beginning, and here are 0.6 inches each. And you are applying 50 kips, 50,000 pounds. And you know what happens to the dimensions afterwards. I'm asking you to calculate elastic moduli. How do we do that? Well, to get us started, I suggest that we calculate the stress. Let's say we call this z direction. It can be x or y, doesn't matter. We calculate sigma z. It's just the force divided by the area. Once you have the stress, calculate the strain. Remember the definition from last time. Change in length. In this case, it's in the z direction. Over the original length. That's the definition. Read the problem and calculate stress and strain. Stress in the z direction and strain in the z direction. And you can talk to your neighbors. When we solve examples in the class, it is more like a workshop. You can communicate with each other, you can ask me questions. Don't forget the units. So let me see a few. I've seen one correct elastic modulus. Looking for 2 more. To get the stress, we divide the force by the area. Don't forget the units. To soon become engineers, we need to use units. strain. So when you calculate the area, you see that it helps. When you have a sketch like that, you can easily see what area to use, right? So the new length is 0.5995. The original length is 0.6. Oh, it's in the z direction, I'm sorry. It's 2.007 minus 2 divided by 2. When you think about formulas, how does sentence begin? Don't learn like a strain is delta L over L kilo. No. A strain is change of length over original length. And then you can figure it out. Then you have a sentence attached to a formula. Okay, if you are here, probably you have already tried to calculate elastic modulus. I give you nice numbers in the next slide. So this is for us to be able to work together at the top. Okay. Now, if you have elastic modulus, which I think I've seen already, now we need to get Poisson's ratio. Does anyone have an idea what to do? Idea? Everyone looks down and I just have to learn your name. What do I do? How do I get Poisson's ratio? Yeah. So we need to calculate lateral strain. I'm not sure you find this problem on Google, but you can try it. So look, to find Poisson's ratio, the sentence that we have is the ratio between lateral and axial strain. So we need to get lateral strain. And in this case, we either call it X or Y, doesn't matter. So it would be change in width over the original width. I mean, you can call it something else. It's like a side length or whatever. But what I mean is one of these two sides. And then you can get lateral strain and Poisson's ratio is nothing else but the lateral strain over axial. And we said last time that to make it a positive number, because we don't like negative number, we add a negative here. So this way you can get Poisson's ratio. Let me see if we correct Poisson's ratio. So the width has changed from 0.6 to 0.599 something. So the change is 0.5995 minus 0.6. And there is no surprise that it would be negative. Has to be. You have to always between 0 and 0.5. So if you got something which is not in that range, probably something is very wrong. If you have Poisson's ratio, then the last thing that I've asked here is to calculate shear modulus. How do we get that? So you see that the force is in the direction of the inch, which is the larger one. So you need to know. You need to know what is where is the force in which direction is outlined. You see this in the schematic because two of them are equal and the other one is longer.
No, I'm saying what if the two on top were not?
Then you will be going, then it's going to be a problem. How to get the Poisson's ratio here? Then you have two Poisson's ratio. If the changes will be also proportionally different. So if the material is isotropic, you are going to get the same Poisson's ratio in both directions. If it is not, you are going to get two different ones, and that's all.
So say like a question you asked, if it was shaped like that,
if it is linear elastic, either one should be the same. But this was a Okay, how do I get G? Exactly. If you look at a little bit, it's a slide number 26. And actually, in this case, probably Google would be helpful because this relationship between G and E and Poisson's ratio, I don't expect you to memorize. But there is a relationship between G, E, and Poisson's ratio, which is on a slide number 26. Once you have that, then you can get from E and Poisson's ratio, you can get G. Now, here you can see the nice, that's how I expect to see the homework, the nice kind of write-up of what we just did. Except for G, which I will add at the bottom. So we have stress, then axial strain. Check your numbers here. Then we calculate the lateral strain. Please check your numbers again. You see the negative sign. Then elastic modulus. Check your numbers. Make sure you have the units. And then you get the Poisson's ratio. And at the very end, you can also calculate the shear modulus, which should be around 16,000. What is important is to check your calculations and see if something doesn't match. Why is it? Okay, if you are done with this, look at the next question. So the question here is, you have, it's obviously not a cylinder, so if you have, again, a block of material, plastic in this case, and you place it inside a pressure chamber under a confining pressure of 15,000 psi. And here, elastic modulus is given and Poisson's ratio. And linear elastic behavior. The question is, what relationship holds? And this is a FE exam question, so it's something that may take impact. Now let's analyze this problem a little bit. What does it mean in pressure chamber? What is the state of the stress? Is it uniaxial? No. If you are inside the pressure chamber, it is like being inside the pool, actually sitting. So then you have pressure from all sides. It's a triaxial. It's always good to have a sketch. Even if you are not given a sketch, I suggest that just having a small sketch makes all the difference sometimes. Why do I have the arrows pointing this way? Because it says pressure. Pressure implies compressive stress. So it is triaxial. This is what we can figure out. And we have pressure. And we said in mechanics, we like to make pressure negative. And then we want to see what is the relationship between different strains. So here you need to use generalized Hooke's law. So sigma is equal to sigma x equal to sigma y equal to sigma z, and it is negative 15,000 psi. Or you can make your life easier and say 15,000. Now, you know generalized Hooke's law. Write down the equation for epsilon x, because I want you to calculate the values too in the next slide. And try to see first of all which option here is correct, and second, what is the amount of strength distributed. So here is triaxial. The previous example was uniaxial. Here you need to use generalized Hooke's law, what we reviewed in the beginning of the class. I have to see three correct answers. So talk to your neighbor. There was a good question. Here, pay attention. The stress is given to you. PSI is already a stress, so you don't need to care about dimensions or dividing everything by together. How many people say A? B? Great. C? Great. So they're all equal. If you use the generalized Hooke's law, let's use our convention. And I'm writing everything in KSI. So remember the formulation. It's, let's say in the x direction is sigma x minus nu sigma y plus sigma z. Now, since they're all equal, really doesn't matter. If I calculate epsilon y, I'm going to get the same thing. Because these are all equal to sigma, so all of them would be equal to basically this. Sigma minus nu 2 sigma over e. Now, in your homework, you'll see, if you have looked at the homework problems, you see that there are problems which ask for change in volume. It's a good exercise to also try to calculate what would be the change of volume here. Let me give you 1 minute to think about it and start writing. So the original volume is V0 is 4 times 8. It's 128 inch cube. Now, what is the new volume? So the new volume would be the lengths Lx, Ly, the new ones, Lz. And if we have the new volume, the change in volume, delta V, would be just V minus V0. So what you really need to do is to calculate how much each side has changed. Try to see if you can think about it, talk to each other and calculate it. I don't give you too much time, but a little bit of time to work. Okay. So remember that in every direction we can write the definition of a string is change of length times the original length. So if you want to see how much each side has changed, basically in this case in x and y direction it's the same, and you just have to multiply the original length, which is 4 inches, by the epsilon, which is the same for all of them. That's the change in length. So the new Lx, which will be also the same as the new Ly, will be 4 inch basically how much it was before, and this is how much it's changed. And the number is somewhere here. It's 3 point, becomes a smaller, you are pressuring it. And the string doesn't have a unit, but change in length has a unit. And you can do the same in the other direction, which is longer. So this is change in length. The new length is the original one, which was 8 inches, incorporating this change. And it turns out to be 7.9976. So let's see. We have this is new length. New dimension, maybe I should say new dimension. So now the change in volume will be again the new volume minus the original one. So the new volume now, the two sides are not 4 anymore, they are slightly smaller. The other side is also slightly smaller. And then we had 128. In the homework problem, you see that you are asked to calculate volume change. So it's basically not complicated. You just need to look at. Any questions? Did everyone write down? Should I keep it up? So this is linear elastic material. Now, we want to learn about more realistic materials, like elastoplastic materials. So, what last time we talked about was the distinction between linearity and elasticity. So what you are looking here is different stress-strain relationships for different materials. And you see that at the lower strains, we can think that almost all of them are a little bit linear, some of them more than the others. But when the strain is very small, a lot of them are linear. That means the relationship is a straight line. And you can recognize some important materials here. But then, elasticity is a different thing. There are two important aspects to elasticity. One is when you apply the load, immediately you get reaction. The reaction, the deformation is instantaneous. This is important. And the second one is that it goes back to the original. So either one, if it is violated, the material is not elastic. And last time we said that elasticity, you can think about a loading-unloading curve. Loading and unloading goes on the same curve. So you can have these two arrows going up and down, increasing a strain, decreasing a strain. What happens inside the material is when you have elastic deformation, the distance between the atoms gets stretched. And then when you release the load, it goes back where it was before. How about linear versus nonlinear? Well, that's kind of clear. If the relationship is a straight line, it's linear. If it is not a straight line, it's not linear, it's nonlinear. If it's not a straight line like the one you see here, this is definitely not a straight line. But it goes back on the same curve if you unload. So it's still elastic. If it doesn't go back, and it's not a straight line, it is non-linear and inelastic. So linear means linear, just a straight line. It doesn't necessarily imply that the material is elastic. For elasticity, you need to have instantaneous response and reversible deformation. And here we don't have that. It doesn't go back to zero. It goes back along a different curve, and it doesn't go back where it has started. So it's important to distinguish between linear, nonlinear, and elastic. Now, if we have this situation, if I ask you what is elastic modulus, it's easy, right? What is the elastic modulus here? The slope of this curve. If there is only one, because there is only one line. But if the material is nonlinear, we don't have just one elastic modulus. In fact, at every point, if you calculate the tangent at every point, you are going to get a tangent modulus at that particular strain. So basically, if you differentiate a stress with respect to a strain at every point, you are going to get a different modulus. And that we call tangent modulus. And people for different applications also have come up with other definitions which are useful. For example, initial tangent modulus. If you calculate this derivative at a strain 0, this is initial tangent modulus. And sometimes it's easier to just calculate the slope between two lines. Yes, please. I'm sorry. This one? derivative. So I don't know how you are familiar with it. You can write it as d sigma over d epsilon. And it's a function of epsilon here, because you see that it's changing as the strain is changing. In a more general way, I use this other symbol for derivative, but it's basically the derivative. It's when you differentiate. So if I have sigma as a function of a strain, then it basically the derivative means something like that, right? That's what I mean. And this is actually your tangent modulus. And since this relationship is not linear, if it was linear, this would be just one number. If it was linear, it would be like sigma equal to E epsilon. And then I would just take the derivative, and it would be always E. But if it is nonlinear, you are going to get a function of a strain. At every point, you can even see, you can feel it. If you take the tangent and look at the slope, it is kind of changing. Right? In the beginning, it's larger, and as you go here, it's getting smaller. That's the nonlinear behavior. And then you have the chord modulus between 2 points. And if the first point is the origin, it's the second modulus. These are just the definitions. Any other questions on this? So when we have nonlinear material, basically strain is, the elastic modulus is not constant. Now, again, for emphasis, look, you can have linear elastic and really nonlinear, but it's still elastic if you come back on the same loading unloading curve. But what happens inside the material? If you pick a very small element and you have a way to look into atoms, and we do have a way now, we have microscopes which can actually see what's happening between atoms. You see that if your material is elastic, if you load it, the distance between the atoms is changing. But when you unload it, it bounces back. But when you have inelastic deformation, this is not what is happening. So when we have inelastic deformation, up to a point, yes, you're stretched. And then after a certain point, after reaching the end of this linear elastic regime, elastic limit, you start having shearing planes within the microstructure. These are called slip planes. So it's like a slippage. It slips inside the material. We don't see it. What we see, what we measure in the lab, is this behavior. It's not going to go where it was going before. And now, when you unload, these breakages, they don't go back. So that's why if you unload the material after passing this point, you see that you are left with some plastic or inelastic deformation. This is a very typical behavior of a structural steel that we see. Any questions about this? Materials are neither fully plastic or elastic typically. You are somewhere in between. So just like the one I just showed you. Beyond the elastic limit, everything is reversible. When you pass that point, it's not anymore. It's probably, and you know now it's skewed what? If you pass a certain point, the atoms don't go back. You have dislocations and you have slip inside the material. Now, if you look at a stress-strain curve, which looks like this, and you may have seen it before, it's very important to understand what's going on. So let's look at this curve together. linear elastic, and you can very nicely measure elastic modulus up to a point which is called elastic limit, which can be a proportionality limit. Up to this point, everything is linear elastic. And then you see nonlinearity. Now, if you unload, it's not going to go back like this again to be linear. Still, it doesn't. It goes back parallel to the first line, meaning that this slope is also E. It goes back. So you have this much permanent deformation. Now, the interesting thing is, if you load again, it's going to actually go all the way linear elastic until A. It is as if you have elevated the elastic limit. You have hardened the material. It goes higher here. So you have changed the elastic limit. And those texts actually explains to you what I just told you. This should be familiar to you from strengths of materials a little bit, if you remember, right? And now, if you think microscopically, what is happening is exactly what I was explaining to you before. After passing the elastic limit, you have slippage inside the material that it doesn't go back. So before letting you go, I want to explain a little bit how to solve this problem, because I want you to work on it before coming on Monday, so you have already worked on it at home. So this is a stress-strain diagram, and there are 3 questions asked. You have a stress, you have a strain, and it is a bilinear. It's a bilinear elastoplastic behavior. So you are asking, I'm asking how much would be the strain if you load it to 650, and what happens if you unload it? It would be, so next time when you come on Monday, try to, before coming, look into that. So what you need to do is to calculate these 2 elastic moduli and basically work this problem. Remember that there is a quiz on Monday. The quiz will have 1 question, 1 problem about everything you've seen in the past 2 weeks. It's not too bad. Question? It's not open though. Not this one. Some of the concepts like Poisson's ratio you need to know. I don't expect you to know the relationship between G, E, and Poisson's ratio, no. But you need to know what Poisson's ratio is. So.
I have a question.
Sure.
I tried to did